I am excited to introduce the following session. We have Euclid's Elements for High School Classrooms, presented by Miss Faith Hoppen. She is a middle school math teacher at Lifegate Christian School in Omaha. She has a master's degree in mathematics from the University of Nebraska. She focused her studies on geometry, which stemmed from her time at Black Hills Lutheran, where she was able to successfully implement Euclid's Elements in a classroom setting with high school geometry students. Please welcome Ms. Hoppen.
Thank you. Welcome. Okay, so here's a little bit of my history, but I had taught at a Christian school, Lutheran school in South Dakota, and we switched to being classical partway through and realized that the secular geometry textbook given to us for free by the public school wasn't going to cut it. And so found Euclid's Elements. I hope you've all maybe seen it, read it. It's an easy read. But found it and just kind of dove in and realized this is accessible for high schoolers. It's workable, like we need to be using this and getting away from the whole idea of memorize this, do this. And so that was kind of the thought on it. And then I moved back to Omaha, and now I teach middle school math. So we don't do this every day, but I was getting my master's degree and trying to determine what I should do my thesis on. They said, what are you passionate about? I said, I'm passionate about this. Like, let's do Euclid. And so it's been a fun, exciting opportunity in that program. What we're kind of talking about today, and we're going to do a little bit later, is the first half of a year-long curriculum using Euclid's Elements. So that's kind of the idea. Okay. I did bring it in, but hold on. Yeah. Okay. So, by and large, Euclidean geometry is presented from the perspective of 20th century philosophy of mathematics as a set of sentences that follow from axioms, and as a result, students implicitly adopt a view that mathematics is an endless chain of theorems governed by logical consequences with no beginning and no actual aims. And so this resonated with me. I think back to my high school geometry class and think, why did I memorize all those little three-letter congruence theorems and things like that? Because in the real world, I didn't use them until I became a teacher. And so the whole idea of this is returning to the beauty of mathematics and returning to that idea there. So what's the problem? Can I get a show of hands? How many students have said, I'm never going to use this? Or, this is ridiculous, why are we doing this? Yes, we get it every single day. And so, the whole idea is, let's not necessarily focus on when am I going to use this, let's focus on the pattern of learning and the beauty behind geometry, and honestly seeing the simplicity in which Euclid wrote this. I mean, he used five things that he held true. He said, if we can all agree on these 5 things, I can prove everything in geometry. Okay, and so it's just incredible. Actually, I don't know how many of you are that familiar with Euclid, so we're going to take a minute here. Maybe we're not. All right, so he said to draw a straight line from any point to any point. I think we'd all agree that can be accepted by everybody. He said to produce a finite straight line continuously in a straight line. Once again, I think we can all agree. To describe a circle with any center and any distance. That all right angles are equal to each other. And this postulate number 5, it's a little controversial in the geometry world, but it says that if a straight line falling on 2 straight lines makes the interior angles on the same side less than 2 right angles, the 2 straight lines, if produced indefinitely, will meet on the side in which the angles are less than 2 right angles. So parallel lines there. And so he said, just let me say 5 things. If we all agree on those, I can write 13 books. I can say 465 things about geometry that are true. And so it's just, I think there's a moment of like recognizing history in that and recognizing beauty in that and then recognizing art as we look at this and oh, it's just amazing. So. Robin Burlew here says, we have to give them something even better to love than the grade. If the grade is the highest, most pleasurable thing that comes out of this learning, we've lost. That one kind of hurts. How many times do our students come up to us and say, oh, Ms. Hoppen, I need an A, or I need to be able to pass so I can play basketball this weekend? Well, we need to learn. Like, our goal is, the grade, yes, it's our representation of their learning, but they're so focused on the grade that we miss out on what's behind it. So, history, if you grab a packet, you've got this. We're not going to go too in-depth here, but we were using Euclid's elements all the way up to 1860, and then William Whewell there said that geometry is a permanent study, but we need to use progressive studies. So we're going to focus on algebra and calculus. And then we had James Joseph Sylvester, who just came in and said, I didn't like geometry, and so let's not use it anymore. And those two kind of partnered and found some other friends to get together and not use Euclid. They wrote a textbook that superseded Euclid. It wasn't Euclid's elements. Then we go on, I mean, you can read it, but Anti-Euclid Association. That's rough. You literally used his name in your title. And then we get in 1884, the elements of plane geometry. So you still call it elements, it just wasn't Euclid's elements. And then 1888, Oxford and Cambridge, the two big guys at the time, said, you know what, we like this, let's do this. And nobody got an issue. So then opposition there, people coming back and forth. But 1860 is really where it started, and now you do not see this in classrooms at all. You see the big textbook says geometry, it's got some funky shapes on the front, and everybody, you have to memorize so many things per chapter in order to do well on the test. And so we still teach Euclidean geometry, we just leave Euclid out of it. Okay? I am very happy that the history teacher at my school does talk about Euclid, but I don't think I had heard of Euclid until, college, when somebody told me that we were studying Euclidean geometry. I didn't know, I just knew it was geometry. And so there's beauty in that history behind it as well. So, I'm so sorry, I think I actually left these in my car, but the material, that's a bummer. Okay, the material includes, this is what I was doing in my thesis, it's a student workbook, an answer key, a teacher guide, and then quizzes. Those are the resources I use for it. These are two of my students, them up at the board, showing us how to do some propositions there. This was when I was teaching in South Dakota, so these are high school geometry students. The data that's collected that's in your printout there is from my current middle school students. So since they're middle school, I really couldn't do a ton of research with them. But we did 3 of the propositions on parallel lines and transversals, collected data there, and using the whole Socratic method, let's sit, let's have you read the proposition, you present the proposition, you have to own the material, saw major improvements from pre-test to post-test there. If you like statistics, the next slide is for you. We're going to move on. So, in the curriculum that I had created, and that you will be doing a little bit of in a minute here, the first semester is book 1, 2, and 3. So book 1 of Euclid's elements is all the foundations that you need to do the rest of it. Book 2 uses that and actually introduces some geometry. Then book 3 is all on circles. And then in the future, we're going to have the rest of the curriculum. Books 6 through 9, 11 through 13. Certain books and certain propositions are left out due to time. This can't be a 2 or 3 year class, although it would be fun. We can't do all 465 propositions there. So, it's in your printout if you really want to focus on it. If you want to read it at your free time, feel free. We don't need to go through everything here because I do want you to have some time to work with this. But the whole goal of this is obviously students who have completed algebra, they're in a normal 9th or 10th grade geometry class. If your students have done rhetoric or debate or logic, amazing, amazing. Not all schools do them, and so it's just a step up for them, but the first chapter or 2 of the book does work on logic there for those that are missing that component in their daily class material. But the whole idea is that it could be seen like this, I usually say round table, the opposite. but it said you two are doing Proposition 1, you two are doing Proposition 2, you two are doing Proposition 3, and tomorrow you're all presenting to the rest of the class on what you learned. And so it's the whole idea of you have to own this, you have to know it, and you have to be able to defend it when you get up and present your proposition. And so that's how it's laid out with that. So each student is expected to participate, be an active part of the class with that. Feasibility. Each kid should have a copy of the elements. They should all have a student workbook, and then there are work bags that are sitting out, and they should have like a compass, maybe a ruler, protractor, stuff like that in there with that. So, okay, so like I said, I've written the first semester of this, the second semester I'm hoping to finish by May. Material to be tested in classrooms. If any of you are high school geometry teachers and would love to help me out, I'm calling on you because I teach middle school right now. So hoping to test some material in classrooms for the next 2 years, to edit some material, revise it, and then be able to publish this by 2027. There are Euclidean classical geometry books out in the market, but I haven't seen any that have like an interactive student workbook that ask for the Socratic and student leading. And so that was kind of the thought behind this, was to truly lay that out. Could be used by a classical teacher or possibly by a regular teacher, a public teacher, Lutheran teacher, whatever. So that's the thought with that. So, if you'd like to be a part of helping me out, you scan the QR code, or you've got the QR code on your printout there. With that. Okay, any questions before we get into doing some hands-on? Yes?
Have you heard of the Arts of Liberty project?
No, tell me more.
I'd have to email it to you. They have a workbook of sorts, and you might want to look at it.
Okay, thank you. Yes?
When you have the grouping of students presenting the different propositions, do you then rotate so that they all present them all, or do they only present some of them?
They only present some of them, but like with the workbook, they're all doing them all. They're just not all presenting them all. Yeah, yeah.
How do you have, so you were saying like one group's doing Proposition 1, one's doing Proposition 2. How do you have them do that simultaneously if like say you need Proposition 1 for Proposition 2? How do you deal with that kind of stuff?
Okay, so they're all doing them all. It's just certain groups are presenting them.
Oh, okay, gotcha.
Yeah, so like we'll spend 3 days and we'll all do Propositions 1 and 2 individually, and then certain people will get up and present. So the whole, I mean, you as classical educators know we want people who can argue well, argue respectfully, okay? And so that's the idea of like getting up and being able to speak and argue and present with that. Okay, so if you are not, people who have little bags, you'll hold them up. They have the materials that we need. So if you're not sitting by a bag person, please move to sit by a bag person. And I'm gonna hand out another handout, and we're gonna do some work.
You're our group. I guess it is. I guess we are stuck.
Position.
3, 4, 5. Yeah, we're gonna have to share some printouts too. I really did scope it.
Yes, please.
Can I take this chair?
Yes, please. Okay. I don't know. What does it say? I got 2 more.
Okay, she's got two more people want handout.
Sacrifice.
No, you should participate. Maybe one more up here. Okay.
So my husband caught us.
So,
Full chairs.
want you, what you have in front of you is you have Propositions 1 and 2 from Euclid's Elements, and then you have the workbook pages from Propositions 1 and 2. And so I'm going to give you time here. I want you to use the space provided to go through the proposition and draw it out and understand what's happening in there, and then answer the questions below with your group. for these? Does it take? So this one says, for proposition 1, says describe circle BCD with center A and radius AB. So draw a circle. That's how we start, draw a circle. It has to have a center A and a radius AB.
So we have the same, oh, we
So
have.
it says to draw another circle.
Yeah, so,
Sounds like we're right on time then.
oh, no, I have one. Oh.
Okay, no, sorry, you can use the screen. You can't better. Euclid.
Circle around A.
All right.
Erica's got it. There, you could ask me, they do that on the sheet for section. Sometimes I rotate the paper.
Hey, there you go.
Center B and radius B. Okay,
So now I just move the center over. Now they just the edge of one circle is the center of the other.
Are we just supposed to create the picture from the beginning?
This is now.
Okay, so we just have to, we want to make a triangle from circles.
Yes.
So if you have,
It's not right.
It's bigger than what it was. That's okay. It'll fit.
yep. Now, so basically, if all you have is a compass, make an equal front.
Well, I mean, just at the elementary.
Oh, gotcha. So actually, you're going to but you can still. Yeah,
So my knowledge when you it says two things are equal to each other.
So now we gotta use
These are
you guys construct over there too. So, how do we know if you use but there's a center of one, so
Right. So by definition, they have to intersect twice.
Because AB is the radius of the circle, and it's the radius of the other circle, and the other radius would be the same length. So AC of BC.
okay, sure. Okay, so.
See, but you have these
Because they share a radius.
The center of
Right out in the order of equality.
unless they have it.
The opposite end of this, it's clearly not. Right, and this one's inside the circle. If you're going this way, going outside the circle, you have to cross inside. Similarly, coming from this side, if you're coming around, going from outside the other circle, inside the circle, it has to be a little different.
AC equals BC.
2 points whether
Because AB
Now, if you took circle, that's how I know
This is the argument.
it's just the thing that they all kind of I guess you could think about the rules of the circle. Yes, yeah, that. And how a circle relationship. Yes. This circle is that, yes. Say, why did I fix it up this way? They would never do
Oh, same on both sides. Oh, we did that.
We did that.
But you have to act on the same plane though, because you define that the circle had you define that it's had to cross in the direction that you're going. But the second circle had to have radius.
Yeah, but you could have had radius like this.
It's really good. It actually sounds really
Well, no, because A and B are both points of space. So they're not, so AB is not just a unit thing. It defines the words. We went over that. It defines B on the first one, it defines A on the first one. So it forces them to do it.
I thought we failed.
We got.
And now we're
Yeah, so it was like we did it for real, and then we just okay, no, we're just doing it because there was so much. So maybe you said this and next year.
Yeah, what it was is that you confirm so since AB and BC equal each other, we know that
We need to make it.
Okay, so you are trying to squeeze in all.
we know that
Or sorry, no, quickly. Okay, yeah, that's good. Hey, I like that. Good.
Once you get it, spin the compass,
Probably say something like this.
We're fine. Thanks. We're super proud, right?
We need, we're given this one.
so since AC equals BC, we've already proved the other side.
Well, that's where okay, and then we have another point. Use those things.
All right, should we move on to proposition
folks
2?
through, that's why. There's some give. Maybe that's enough. Oh, is that enough? Not quite.
This symbol here is this.
Yeah.
Someone else want to do this one?
Okay. Triangle. Yeah.
Triangles are going to be different because
So if we just have
I don't think
Drawing the straight line. Produce the straight line.
you're saying it's wrong.
Okay, can I have attention real quick? I will let you keep working, but I don't know if you guys noticed the little things in blue on the side. Those are Euclid's like reasonings for why he was able to do everything. So like this one says 1 post 3. That means it's the first book, postulate 3. Okay, and so those are all of his reasonings. So if you don't know Euclid or have Euclid with you, like the CN1, that's common notion 1. So that's something that the students would have already memorized with that. But you as mathematical minds can kind of make some links in there without actually knowing them. So he does have reasonings for why he's doing everything. I want to call that to your attention. But you're all doing great. Keep going.
That's what my career.
Oh my goodness!
we need to put a line the same.
Now it says straight lines to be.
We have C. Okay, so that's your radius. Sorry, DC is a radius.
Well, an exercise reminds that
Oh, yeah.
bring it back.
And so certainly can you.
Yeah, you can go down with the, yeah.
But we actually have it,
That's an arc length, this, so that you can come over.
he's got more.
Wow, you did that pretty well. I followed your back. Well, I don't know what you can say. That's
G would be the point.
It's actually,
Then the line.
I totally freehanded it.
I wonder if we want them to
That would be G.
straight line, right?
Right.
With one end, I mean, an egg, so right
So
there.
if you, so one and one, so if we take.
How did we answer
Or is it we're going through.
So it's on from A.
No, because
It means some sort of
B, so now G is our radius.
Yeah, and then draw that, and then draw that line.
Is that C? No, that's not C. I don't think it's actually.
It's just a line.
how should the well, we know the
But I think, I
Now we gotta do equilateral triangle.
Pastor Castelleros. Size for our town.
We need to label the
I've been in the school. Fifth year, but second year teaching.
Oh, you haven't done it?
created
Yeah,
it.
okay, yeah. I thought this was.
yeah, I teach and you're a grim.
So this is now point
BG equals the DC. So we have drawn a line.
I grew up with my like, why did they do sidelines? Both the schools I went to were all
So we talked.
Our savings first non-single church I've ever been in.
Did it says they have to do
Just produce.
The first equality that we get is
So this is.
Then we draw.
Out over here.
Yep.
Okay. So this is F out the structure.
Next bigger circle.
A straight line, yep.
That's awesome.
And we have two radii, CC and G.
Down in middle school this year, I like
Then we
that.
draw the final circle from get EL and G are equal. Since AD and D are equal, that AL, G happens to be.
No.
Okay, right, so. Well, and there's some original stuff like in the, around the church.
Oh, how frustrating. I feel like you've done so well.
Yeah. Okay, sweet.
Alright, so we've got BF and A. We're supposed to do
So we're expecting that to never happen. We feel very lucky.
wait, CG. Or G. So the center's B. Okay.
I don't know. I mean, there's a Lutheran high school in West Michigan.
So,
Maybe 20 years now. So it's not super.
It was part of our.
So this is
Hold on.
you're talking about these two.
Oh, and describe.
And so your theory,
What people in the 1800s like about Euclid? Why? It's learning new access tech. So it's sort of in your mind.
I think, are you saying learning the facts of like just memorizing some of the Yes.
I don't do
Yes, and so I think we should go into this where they like actually dive in, their hands on, their feeling, and their decision. It changes everything. Yeah.
To begin with, or
Well, it's like.
Only the, well, no, that's perfect.
Yeah, so there's.
Oh, sorry. Okay, yeah, because, I mean, there are some that are being created, right?
That's true. Yes, the picture's helpful.
So CGH, get a little bit but otherwise,
yeah, you should do it. No, they would have
okay,
that was our goal. Just make a line.
I've only been there.
This is like.
everyone has to learn techniques. So I wrote a thesis. Which was a requirement. It was on migration. So I'm also very much involved in the putting it
Okay, so L is
Oh, yeah.
But this time, he'll memorize.
so circle is KG.
So those are kind of obvious, but like.
What's the one where
my wife's grandmother lived. We still have stuff in storage there, right? We've been living in an apartment in a house contract. So, Mary drove the kids home on Saturdays to their grandmother. I drove up to Oklahoma City after church on Sunday. We met there. We dropped them off. Picked up their moms in
L and BC. Yeah.
Where are you from?
Number
All that's so let me actually hear.
Until L or L.
Down to final thoughts, we'll share on them in a minute.
It's kind of like, yeah. And then geometry.
Equals
Okay. So, I know I said I left them all in my car, but I didn't. I found them. So, if you want to see the quizzes and student workbook, he's got the teacher guide, he's got the answer key. They're up here. You can take a look at them if you want to see what's going on with those or kind of how it's laid out. So it doesn't look quite the same as what you're looking at, but the same idea. So like in the answer key, it's all drawn out and then suggested answers. Although if you're a geometry person, you should be able to solve the propositions on your own, but suggested answers are given. So with proposition 1, I saw a lot of successful drawings. That was good. The question says, how do we know that the circles will intersect? So does anyone have a thought that they want to share on why those circles would intersect and how you know that?
They share point C, like by definition.
What did you say? I'm sorry.
They share point C.
They do share point C, yes, so they have to intersect because they share the same point. Any other thoughts? Yeah?
The endpoints are the center of each circle.
So if they're in both circles, they have to intersect, right? Yes.
As the radius, they're both equal to each other.
There you go. Yeah. And so we bring all these different ideas, and whoever's presenting, you probably would have made your idea a little more prevalent. But there's beauty in getting the different ideas throughout the room because there's not necessarily one, like, this is the only reason to intersect. And then coming back to that, I don't know if you guys remember, I read postulate 3 to you about 20 minutes ago, and it said we were allowed to describe any circle, any center, any distance. And so that's kind of where that comes from, is we can describe both these circles with whatever center and whatever distance we want. So, okay, number 2 said, how do we know that segment AC equals segment BC? Therefore, segment AB equals segment AC equals segment BC. What's that? They're equal to the same thing or equal to each other. How do you know that? There you go. Nice job. Yes. Yep. It says by combination. Well done.
Is common notion the same as axiom?
No.
What's, just on the terminology, what's the difference?
I don't know. Let's see here. Euclid doesn't use axioms. I would say those are probably propositions and is use postulates, combinations, and those propositions for the. Okay. I think a lot of you attempted proposition 2. Maybe some successfully. Okay. I think this group back here, were you successful in 2? Is that exciting? Maybe. No. We have a group of non-math teachers putting their best effort in and having good attitudes. Okay, so write out the order of equalities that were established through this proposition. I have 5 of them.
Is it order of equalities or equality? Because ours says order or equality.
I was just like of equalities. Sorry.
Okay.
Of equalities.
Okay, Dad. Okay.
Yes.
Yeah.
Yeah?
Alright. BC is equal to BG. Definition of circle. BG is equal to DC. Definition of circle. BD is equal to DA, proposition 1. BG is equal to AL, common notion 3. And AL is equal to BC by common notion 1.
I had DL equals D is congruent to DG. And you said DC, I think?
Say again, sorry.
I said DL is congruent to DG.
Oh, maybe it was DL. Yeah, that's what I meant. Yeah,
DL?
you're right.
Yes. Okay.
No,
Yes.
DL is equal to DG.
There you go.
That's what I have written. I guess
That
what
looks like a
it
C.
is.
Yeah.
I see. I misread my own writing.
You're just like a high schooler.
I
Yes.
had seen that. So,
Okay, so now you've all experienced it. Thoughts? Do you think this is attainable for certain students? Does this look like something that your kids could do? What do you think?
I have a question. So
Yeah.
you said that they would know the postulates?
Yes.
So what does that look like, or when do they learn
Well,
that, or
I've
how?
got my book of quizzes up here.
Okay.
And so they need to take a quiz on the first 26 definitions and the postulates and the combinations before we even start the propositions.
Okay, so is that something that's like a class period, you bring those up? And
Lots
then,
of memorizing
okay.
to start, yes. Yeah.
So is that kind of how the year starts out?
Yep.
Okay,
Well, actually, I take that. We start with a unit on logic,
okay,
and there's a unit on like history of Euclid.
okay.
So, but then it hops into book 1, and with that. But book 1 has the most definitions. So I think book 2 only has like 8. So that sounds better than 26. So it just gets better from the first
Super
one.
interesting.
Yeah, but once you have those basics down, then you can do so much more with them. So,
Do you have the students label them by common notion 1 or postulate 3, or do you have them name it like all radii are equal?
no, I wouldn't label them by what they are. But you could do it differently. You don't have to do it the way I say it.
Wait, which one do you do?
Yeah, which do you do?
I do like common notion 1, like CN1, or postulate 1, because they have their workbooks, so they can flip back in it and say like, oh, this was from book 1, postulate 2. That's what I should reference. So,
You use Euclid for high school?
yes.
Did Euclid write it for that level of student?
It was the main math textbook, so it was written for anybody who did math as a choice.
Do you think they started younger way back then, or do we know?
I'm not a history teacher.
No.
I don't think a lot of people probably chose to do it unless they were in university. That's kind of my thought on it, because Euclid had his own university at the time. So.
But in all likelihood, maybe
Maybe.
start a little younger.
Start reading this as a
University-
whole.
Their university probably,
Probably 15-year-olds.
yeah.
Yeah.
So I just had back to what I was just asking before.
Yes, sorry.
No, you're fine. My thought is, because as we're sitting here, I mean, some of us teach geometry.
Yes.
Some of us haven't done it for a while, but we're here. But even if you've memorized it in your high school class, I'm not sure, 10 years later you would say, oh, that's common notion 17 or whatever the number is.
Yes.
I think there's some advantage, although it's more writing, I think there's some advantage to having kids, even if you could, maybe abbreviate or whatever, having them write all radii are equal, or, we do a few acronyms like, CPCTE, corresponding parts of congruent triangles are equal. But just so that, because we're using Jacobs right now, and they have like, theorem 27, and postulates. I don't have them memorize the numbers of the theorems and postulates, because I don't think it's as useful for them carrying forward. Because they really need to carry the concept forward, not the number of the label.
Yeah. So when we get into like the circles one, we switch. So what you guys did was you drew it out and then answered questions. But later on in the circles, they draw it out and then they have to write what happened and how they justified it.
Okay,
so that's kind of the thought on those. Yes. Yeah.
And it does sound like the way you have them teach it, if they just say common notion 1, you might, people in the audience could always ask, what does that mean?
They should be, yeah.
Like,
anybody in your class should be able to tell you what it is.
Yeah, I mean.
Yeah, yeah. So once again, yeah, it's hard also to get kids to memorize things, but if you have a good attitude, if you make it sound fun, they might do it.
Candy.
So,
Candy.
No, we don't bribe children.
Sometimes.
But I did want to actually bring this up. Some of my questions came from this book. Dana Densmore wrote some questions on the first book, and so some of my questions do flow from that as well. They're not all just from my brain. So, just a thought there. Okay, you are welcome to take these with you. Keep them, practice again and again. I love my little tools back. Other than that, yeah, if you want to see any of these, they're on the table up here. Take a look at them. Thanks for coming.